Okay, we are taking a look at Unit 3. We are still looking at intermolecular forces and their properties. This is Topic 7, looking at solutions and mixtures. So we've looked now in this unit at solids, and now we're jumping into the liquids and how we create solutions. So our objective molarity is used to represent the concentration of a solution and can also be used to determine the molarity of a solution by dilution. So solutions. A solution is composed of two parts, the solute and the solvent. The solute is the substance that is being dissolved or dissociated. Dissolved being with covalent compounds or things where intermolecular forces are interacting. Dissociated is when our ionic compounds are dissolving. A solvent is the substance that is aiding in the dissolving process. So it's helping the dissolving to occur. So for example, a solution is made of sucrose, which is sugar essentially, and water. So we can see that in the picture on the top right. The sucrose is dissolving, so it is the solute. So those are the larger red and white molecules there. Those are sucrose. So normally in a piece of sugar, those would be stuck to each other through intermolecular forces. But the sucrose is dissolving and separating into the molecules. So it is the solute. The water is helping the sucrose molecules to separate from one another by interacting with them and attracting to them through intermolecular forces. So it is the solvent, it being the water. Another example is a solution is made of table salt, NaCl, sodium chloride, and water. The NaCl we can see in the picture is dissociating, so separating into its ions. So it is the solute, it's what's breaking apart or separating. The water is helping the sodium chloride ions to separate from one another through attractions. So it is the solvent. And it's a good idea to take note of the direction those ions are facing, or excuse me, those water molecules are facing. Think about those positive and negative ions and how they're attracting to those water molecules and their dipoles. Molarity. Molarity is a way of measuring the amount of solute in moles per volume of solution. So molarity is equal to the moles of solute per liter of solution. And that is how the equation is written out on your equation sheet. So you might check out your equation sheet and find that on there. What we're more familiar with seeing is this, molarity equals moles per liter. And that's really what we're going to be using. So for example, it says find the molarity of a solution made from 5 grams of sodium chloride dissolved to make a 150 milliliter solution. So if we want to do this, we need to be able to plug our values into our equation, moles over liters. And we don't have either of those right now. We do have grams, which we can change to moles. And we do have milliliters, which we can change to liters. That one's a little easier. We're going to divide by 1,000 or move that decimal 3 places. So we have 0.150 liters. But we need to do a little more math to get our number of moles. So if we have 5 grams of sodium chloride, we need to change that into moles of sodium chloride. And we do that with the molar mass of our chemical. So we're going to add up the mass of sodium and the mass of chlorine. Sodium has a mass of 22.99. Chlorine is 35.45, so we add one of each of those, and we get a mass of 58.44 grams per mole. So our number of moles is 5 divided by 58.44, and we get 0.0. We got 3 significant figures, so 856 moles of sodium chloride. So that's how much we are dissolving. So that's going to go up here at the top, our number of moles, 0.856 moles divided by liters. So our molarity is 0.856 divided by 0.150, and we get a molarity of 5.3 sig figs on each, so 5.71 molar NaCl. So that's how we would
solve for molarity. We need the moles of our solute, what we're dissolving, per liter of solution. And the way we read this is 5.71 molar sodium chloride solution. Okay. Let's take another look at another example. So many times molarity is used to help us find the moles of a chemical. Most chemicals we deal with are not solids, but our solids have been dissolved in water to form an aqueous solution. Remember, aqueous means something dissolved in water. So in a lot of our questions that require you to have moles on the AP exam, they will give you the molarity of the solution and the volume of the solution, and then we calculate moles using those two pieces of information. So let's take a look at our example. A student measures 25 milliliters of a 0.15 molar magnesium chloride solution. How many moles of magnesium chloride do they have? So we can see this example, we have volume, we have molarity, we want moles. Okay, so let's take a look at our equation. If molarity equals moles over liters, if we want to solve for the moles, we would need to multiply both sides by liters, so they cancel on the right. And so our number of moles is equal to our volume in liters times molarity. So we're going to set this up. We need our volume in liters, so we've got 25 milliliters. We can divide that by 1,000, and we get 0.0250 liters. And we're going to multiply that by our molarity, which is 1.50, our concentration of our solution, molar, and this is going to give us our moles. So we have 0.025 times 1.5, and we get 0.0375. There's our three significant figures. And this is our number of moles of magnesium chloride. Okay, the reason we get moles from this, remember, is this capital M represents moles over liters. So the liters cancel and we're left with the moles. So that's another way to look at those units. So that's our moles of magnesium chloride. So if we're given a situation where we're given the volume, so we know how much we're measuring, and we're given the concentration of the solution, then we can find out how many moles of that chemical we're actually measuring into our container. The next thing we can look at as well is the molarity of the ions. So we can find the concentration of each ion in the solution. When ionic compounds dissolve or dissociate, they separate into their ions. So we practiced this in Unit 2. For example, if I took that same magnesium chloride and I wanted to see what ions it formed, I would separate my two elements, magnesium and chlorine. I bring my subscript to the front. We have two chlorines, and then we have their charges. So magnesium has a 2+ charge and chlorine has a negative charge. So there's my ions that I form. I form one magnesium and two chlorine ions. So if we know the molarity of our whole solution, we can also find the molarity of one or both of the ions. So for example, it says, what is the molarity of the chloride ion in a 0.46 molar magnesium chloride solution? So if we imagine this solution, okay, when we break this chemical down, when our little ionic compound that's in its really lovely little structure, when it enters the water, it's going to break into our magnesium with its 2+ charge and two separate chlorine ions with their negative charge. So for every one magnesium, I get two chlorine ions. All right, so when this formula breaks apart, we have magnesium chloride, one magnesium, two chlorines, and then magnesium chloride, magnesium, two chlorines. So we're always having twice the amount of chlorine. So if our chemical has this concentration of 0.46 molar, for the whole chemical, we can break it down just like we did up here and say, okay, well, let's use the same ratio. When one magnesium chloride broke down, I got one magnesium. So I would get the same concentration for my magnesium. But when this breaks down, I get twice as much chlorine. So I'm going to double my concentration for my chlorine. So 0.46 times 2 is 0.92 molar chlorine ion. That's my answer. Okay, so when I take the molarity of my compound, that's for the whole compound, but we can keep that same ratio, a 1:1 to 2 ratio, just like we have up above. One magnesium chloride forms one magnesium and two chlorines. So if we keep that same ratio, we can find the concentration of any of our ions. And we can also work backwards and go from something like chlorine to our magnesium ion or to the magnesium chloride. So it says if we know the molarity of one ion, we can also find the molarity of the other ion or of the whole solution, just like I said. So let me switch colors here. So it says, what is the molarity of a solution of sodium nitride if the concentration of sodium, so our sodium ion, is 0.23 molar? And then what is the molarity of the whole solution? So the easiest thing for me has always been to just write my chemical and see how it breaks down. So I've got sodium and I've got nitride. My 3 comes to the front, so I have 3 sodium for every 1 nitride, and nitrogen has a 3 minus charge. Okay. So I know my sodium's concentration is 0.23 molar. So if I want to go from sodium to nitrogen, it's a 3:1 ratio. So there's 3 times as much sodium as there is nitrogen. So I'm going to take my concentration, 0.23, and I'm going to divide it by 3. And I get 0.077 molar. Okay, so we can also go the other way. If I have 0.077 molar, then for my nitrogen, then my sodium should be about 3 times as much. So if I multiply that by 3, I get 0.23. So we can go back and forth between our 2 ions. The other thing we can notice is that our ratio of sodium to our whole chemical is 1:1. So those should have the same concentration, 0.077 molar. All right, so we can go between any of our ions or our whole solution to find their concentration. So our concentration of nitrogen is 0.077, and same for our whole chemical, sodium nitride. So we're just using those coefficients. This is one of the many reasons why we practice so much of splitting apart our ionic compounds.
So this is how to make a solution. So if we want to actually create one of these solutions with a particular concentration and particular volume, we would go through this process. So first, we will weigh the calculated mass of the solute on a balance and add it to a volumetric flask. So these pictures here are showing us different sizes of volumetric flask. We use those because they measure one volume very accurately, very precisely. So for instance, this larger one on the left that says 250 milliliters, it would measure to the line up at the top there. So our line here is our calibration mark. So at that line, it would measure 250 milliliters with 2 decimal places, so 250.00 at that line. So it's very, very precise. So we're going to weigh out our calculated mass of our solute on a balance and go ahead and use a funnel, add it to this volumetric flask. We're then going to fill the flask 3/4 of the way with distilled water. Now this is not an exact amount, just about 3/4, 2/3, around there. And then we're going to swirl it. So we can put a cap on it and go ahead and swirl it around to make sure everything dissolves. We don't want to see any solid in there. Then we'll uncap it and go ahead and fill the flask to the calibration line with distilled water. So you notice that it does not, there's a note at the bottom that the amount of water is not specified. We're not measuring the amount of water at all, okay? And it's because our solute, that solid we add at the beginning, has a volume of itself, in and of itself. So we're just gonna fill it to the line till our total solution volume is 250 milliliters, or depending on the size flask, it might be in the right-hand side, we've got 1,000 milliliter, 500, 250, 100. So we pick our container based on how much of the solution we want to make. What volume do we want to make? Right.
All right, so we're going to take a look at an example of how we do a calculation to make a solution. So a student needs to make 500 milliliters. So that's our goal, how much we want to make, of a 0.121 molar solution. So there's our concentration we want of cobalt chloride using solid cobalt chloride dihydrate. Determine the mass in grams they need to make their solution. So we need to figure out what mass do we actually measure on the balance to then transfer into our flask and dilute using and create the solution using water. But we got to know how much mass to measure. So if we have a volume and a molarity, we can always find moles. So molarity equals moles over liters, going back to our original equation. We can multiply both sides by liters, and that gives us our moles. So our volume in liters, so we're going to move that decimal, divide this by 1,000. Ooh, I moved it a weird number of times. So we get 0.5000. I'm going to keep all those zeros because they are significant. Many liters times our concentration, 0.121 molar. And that will give us our number of moles that we need to measure, 0.0605 moles of cobalt chloride. Now, we need to figure this out in grams, right? We can't measure moles. There's no device in our lab that actually measures moles. We have to change our moles into grams. So I'm just going to switch colors. I'm going to go ahead and, that is a C, set up my conversion. So we want to go from moles of cobalt chloride to grams. Now, the only thing I'm going to be careful of here is it's giving me this formula. It's a hydrate. So if I'm like going into my chemical stock room and I see this, I just need to make sure that when I do my mass here, I incorporate those two water molecules into my mass because they're already present in the container. So we just want to take them into account. So we're going to add up the mass of that cobalt chloride dihydrate. So cobalt has a mass of 58.93. We're going to add to that 2 chlorine, so 35.45 times 2. And then I'm going to add 2 water molecules. Well, I've gotten to the point where I know the mass of water. It's 18.02. And so I'm going to do 2 of those, so times that by 2, and add that to my total. So we should get a total mass of 165.87. Another way you could do this is add 4 hydrogens and then 2 oxygens to your mass as well. So we've got 0.0605 times 165.87, and that gives us a mass of 10 point, we got 3 sig figs, so 10.0 grams of cobalt chloride dihydrate. So that's how much we would have to measure on our balance. So let's see how that looks on the next slide.
So based off of our calculation, this is what it would look like to make that solution. We've got the cobalt chloride dihydrate on our balance. It's weighing out, you can just barely see in the picture that it says 10 grams. So an amount of solute is weighed out on an analytical balance. So we're measuring out that 10 grams. We're going to go ahead, and since we want to make 500 milliliters of it, we're going to use a 500 milliliter flask. We go ahead and add our solid to that flask and then add water so that it's about 3/4 of the way full. You can see that in that picture there. The mixture is swirled until all of the solute is dissolved, and then additional solvent so water in this case, is added up to the mark on the volumetric flask. And so on our mark, if this is my mark, I want my meniscus, the bottom of it, to sit right on that mark, right? I want those to be right with each other so that I know I've got the right volume of water, okay? So how do we change the molarity of a solution that we've already made? So if we have a solution that's already made, we can reduce its molarity by adding water and diluting it. It's harder to concentrate a solution. We can by evaporating water, but it's a little less exact, a little harder to do. So typically we only dilute solutions. The equation for dilution is M1V1 equals M2V2. So what does that mean? Well, it's molarity times volume 1 equals the molarity times the volume 2. So how does this work? So let's just take a look at a solution. It says when we dilute a solution, we are only adding more water, not more moles of the chemical. So in our container on the left, it says our molarity here is 6 moles. So we've got 6 particles there per 3 liters. So 1, 2, 3 liters, okay? So if I calculated the molarity, it would be 2 molar. Now, if I add water to this up to the 6 liter line, I have not changed how many moles of chemical I have in there. I still have 6 moles of my chemical. So my molarity, my new molarity, is 6 moles divided by 6 liters, and that would make it a 1 molar solution. So I've doubled my volume, so it cut my concentration in half. Okay, so going from here to here, my volume goes up by 2. My volume is times 2, but my molarity is half. It's half, okay? Or it's timed by 1/2. So why does this work? If we look at our dilution equation for this equation over here, we would take our molarity of our first solution, so 2 molar, times its volume is 3 liters. And then that's equal to our molarity of our second solution, which is 1 molar, times its volume, which is 6 liters. And if we do the math on this, it says 6 moles, because molarity times volume gives us moles. So 2 times 3 gives us 6, and 1 times 6 gives us 6. So this is telling us that the moles of chemical do not change. That's why this equation works, okay? So we're only changing the volume and seeing what happens to our molarity.
So we're going to use our new dilution equation to find a new concentration. Now, I will go ahead and let you guys know the dilution equation is not on your equation sheet, unfortunately. They expect that this is something you could derive or something you will be able to remember. So we do want to practice this one and commit it to memory, but it's not too bad. So it says, what is the molarity? So we're looking for a molarity of a 18.3 molar HNO3 solution when it is diluted from 10 milliliters to 150 milliliters. Okay, so we've got a lot of things going on here, right? So what I like to do first is pair up any molarities with any volumes that I'm given. So we've got, if we imagine, we've got a solution and we're diluting it. So my first solution should actually have less water than the second one. So this has got to be my 10 mils. This would be my 150 milliliters. And it says, what is the molarity of a 18.3 molar solution when it is diluted? So our 18.3 molar solution is being diluted to a new mystery molarity. So that means I'm measuring 10 milliliters of the 18.3 molar. We're adding water till it's 150 milliliters. We want to know what the new concentration is, okay? So our new concentration, if we're increasing the volume, our molarity has to go down. They are always opposites of each other. So when volume goes up, molarity must go down. So that's something to keep in mind as well. So if we look at our equation, M1V1 equals M2V2. So I'm just going to use these two big beakers. This is the one on the left is going to be my M1V1. The one on the right is going to be my M2V2. Now I want to solve for M2. I like to go ahead and actually put in my numbers for this, just so I don't mix anything up and make sure everything stays paired together. And then we'll go ahead and rearrange. So we're looking for M2. There's our variable. You can always replace it with X if you're more comfortable with that. And then we've got 150 milliliters. Now here's the nice thing. For this, it just says volume. It doesn't specify units. So as long as your units for your volumes match each other, you can leave them in milliliters. You don't have to convert them. So we've got 18.3 molar times 10 milliliters. And then we've got our molarity times 150 milliliters. So to solve this, what I'm really going to need to do is divide both sides by 150 milliliters and cancel those. So my M2 is 18.3, so I'm going to put this in my calculator, times 10 divided by 150. So I get 1.22 is equal to my M2. And let's look at the units. So we've got milliliters and milliliters that cancel. We're left with a molarity. So 1.22 molar. Our chemical doesn't change, so this would be HNO3. And that would be our answer. So we can see it goes from 18.3 molar. We're measuring 10 milliliters of that. We're adding water till it's 150 milliliters, and its new concentration has dropped to 1.22 molar. Since our volume went up, our molarity went down.
So how do we actually dilute a solution to a desired molarity? How would this look in a lab situation? So we would start with something called a standard solution. Sometimes it's called a stock solution, but it's our concentrated solution. Okay, so that's what's in that small flask. And then we have our larger flask. We would choose our larger flask based on how much volume we want to make. So if I want to make 500 milliliters, then this flask would be a 500 milliliter flask. If I want to make 100 milliliters, it would be a 100 milliliter flask. Okay, I choose the flask based on how much I want to make. We would pour, the solution is transferred to the larger volumetric flask. So we figure out how much of our original stock solution or standard solution we need. We pour it into our flask, and then we would add water to dilute it. It says the new solution has less solute per unit volume, so same number of moles but more volume, so our ratio is less. So the color, if you notice, has faded a little bit. It lightens it up because we're diluting it.
We can also use our dilution equation to determine how much of the concentrated solution we need to measure. So if we want to dilute a solution to a new molarity, we need to know how much of the concentrated solution we want to measure. So this is a really common thing that happens for me when I'm making solutions. So if I need to make, say, I need to make a certain amount for our lab, so I have a certain volume, and I know what concentration I need, our molarity, then I need to go to my cabinet, and I'm going to find the molarity of what we call our stock solution, what I have in stock, and I need to figure out what volume of that do I measure to then dilute it. Okay, so this example is a great one. A chem teacher needs to make 500 milliliters of a 2 molar HCl solution for a lab. So I know I need 500 milliliters for all my students to do the lab. I know they need to work with 2 molar HCl solution for it to be safe. So the concentrated solution is 12 molar. So when I go to my stocker, when I purchase HCl, I buy 12 molar because I don't want to buy just a bunch of water. So I need to figure out how much of this 12 molar do I measure in order to make my solution. Okay, so let's take a look. I like drawing these because I think it really puts it into context. So I need to make 500 milliliters, and I need it to be 2 molar. I have 12 molar. So we want to know what volume of that one am I going to measure, okay, to then dilute it to a new volume. Now notice the 500 and 2 molar are paired together. I'm figuring out how much of the 12 molar I'm going to measure for this. Our molarity is going down, so our volume here on the left should be higher than our new volume, okay? Since our volume should be going up because our molarity is going down. So let's check it out. I'm going to use this as my beaker 1 and this is my beaker 2. You could switch them, it doesn't matter as long as you've worked out and paired your stuff together properly. So M1V1 equals M2V2, and I'm just going to plug in what I know. So I've got a 12 molar solution times our volume, volume 1, is equal to a 2 molar solution, and we have 500, I've got 2 zeros there for my 2 molar, and I've got 500.0 milliliters, keeping all my sig figs. So if I want to solve for my V1, then I'm going to need to divide by 12 molar on both sides. And then I can do my math. So I've got 2 times 500 divided by 12. And we get 83.3 milliliters because my molarities cancel. So I'm going to have to take 83.3 milliliters of my 12 molar solution, measure that out, put it into a 500 milliliter container, and then dilute it to the line. And I will have made a 2 molar solution. So this is the kind of calculation I do constantly to be able to make solutions for your labs and for all of our labs that we do in chemistry. So how will we actually go about making the solution? So we would take that 83.3 milliliters, we would measure out 83.3 milliliters of our 12 molar HCl solution, so our concentrated solution, and we want to use something that's going to be precise in our measuring. Typically this is done with either a burette or a volumetric pipette. Those would be best. So we can see a picture of the volumetric pipette on the right. These are great because they have a very precise volume. They only measure 1 volume each. So this one shown would measure 100 milliliters. They're a little bit, take a little practice to be able to use. And they're great if you need some pretty basic volumes, like you need a milliliter, 2 milliliters, 5, 10, 20, 50, 100, that kind of thing. They come in nice round numbers. But we need to measure 83.3 milliliters. So that's not a very nice number. So what we would use instead is a burette. So this is a picture of your burette. It's been cut and then kind of adjusted so you can see both ends. I believe we've seen these towards the beginning of the year. But it's basically a long tube, has measurements on it. It goes to 2 decimal places, so it is still very precise, and you can drain from it however much chemical you need. We would need a larger one so that we could drain 83.3 milliliters. The ones I have typically come in 50 milliliter volumes, but you can get larger ones as well. So you would drain from it so we'd fill this burette with 12 molar HCl. We drain from it 83.3 milliliters, and those would get put into our flask. So we would, step 2, add the 83.3 milliliters of 12 molar HCl to a 500 milliliter volumetric flask. So our goal in the last question on the previous slide was to make 500 milliliters of that solution. That's how much my class needed. So we would need to use a 500 milliliter volumetric flask, since that's how much we want to make. So we'd add our 83.3 milliliters to it, and then we would fill the flask with distilled water to the calibration line. Okay, we'd fill it up till our meniscus hit that line. So we'd want our meniscus to be just hitting that line, making sure we get the right volume. So again, just like when I went through the steps for the previous to make a solution from a solid, here it does not specify the amount of water added. We don't need to measure that. We measure our concentrated solution, and then we simply fill to the line. And we know we've got the exact amount of water we need to make our solution. So that's something that if you're asked to describe the steps of making a solution, we do not want to mention measuring water. We just want to add to the calibration line. So this is a free response question taken from a previous exam. So we're going to work through it. A student has 100 milliliters of 0.4 molar copper sulfate, that's aqueous, is asked to make 100 milliliters of a 1.5 molar copper sulfate solution for a spectrophotometry experiment. And we're going to get into what that is soon. The following laboratory equipment is available for preparing the solution. We've got a centigram balance, so that goes to 0.1 grams. We've got weighing paper. We've got a funnel. That's always handy. We've got various beakers, 10 milliliter, 150 milliliter. We've got a graduated cylinder. We've got a volumetric flask, 100 milliliters. We've got a burette and distilled water. So we've got lots of equipment. Just because it gives you the equipment doesn't mean you have to use it. Okay, so that's something to keep in mind for this type of question. So part A is to calculate the volume of 0.4 molar copper sulfate required for the preparation. So let's think about what we want here. What's our goal? So our goal is to make 100 milliliters of our solution, and we need it to be 0.15 molar copper, 1.50 molar copper sulfate. Okay. Over here we have plenty available. So you have 100 milliliters available, and it's a 0.4 molar solution. So I need to know how much of this 0.4 molar solution do I need to make this new 0.15 molar solution. So we are diluting this solution. Okay, so we want to figure out how much of that we need. So we need our handy dandy equation. M1V1 equals M2V2. All right. I've also seen a teacher, if this helps you, write it as not V2, V1M1. She just reverses it, V2M2, so it looks like voom voom, and she just reminds her students to go voom voom to the molarity. All right, so if that helps you, go for it. So our containers, I'm going to call this container 1, container 2, so I've got my 1s and my 2s. So my molarity is 0.400 molar. I need to figure out how much of that am I going to measure, the volume of that chemical that I need to measure, and I'm making a 0.15 molar 0 molar solution, and I'm going to make 100 milliliters of it, right? So we can take a look at this. I didn't set up with a lot of space, but if we divide both sides by this 0.4 molar, we can get our volume by itself. So we'd have our V1, our volume equals 0.15 times 100 divided by 0.4. 37.5 milliliters. So if we look at that, we say, okay, I need to measure 37.5 milliliters of my 0.4 molar solution. I have 100 milliliters available, so that's probably a good indication that I'm on the right track. I'm not using more than I have available. If I did my calculation wrong and maybe I got a volume bigger than 100, that would be a big red flag to say, hey, I probably did something wrong, okay? So that's how much we want to measure. And so let's briefly describe the essential steps to most accurately prepare the 0.15 molar copper sulfate solution from 0.4 molar copper sulfate using the equipment listed above. So thinking about what we talked about before, first thing is we want to measure 37.5 milliliters of, we want to specify the concentration, 0.4 molar copper sulfate, and we want to state how we're going to measure it. We're going to measure it using a burette, because that, if we look at all of our options for measuring things, we've got beakers, which are terrible to measure with. We've got a graduated cylinder, which is better. And then we have a burette. Okay, we don't have any pipettes, so we're going to use that burette. That's our most accurate. And then we're going to place 37.5, the 37.5 milliliters into the 100 milliliter volumetric flask. We'll always use a volumetric flask for making a solution. Okay, so we're going to use that volumetric flask. Now, it's a 100 milliliter volumetric flask because we want to make 100 milliliters of solution. So that's perfect. Then we will fill the flask to the line. You could say the calibration mark, the line, something like that, with distilled water. Okay, we do not mention how much distilled water, we just say we fill it to the line. We do not have to measure that. You could mention using the funnel, that doesn't hurt. We could say using our funnel to help deliver the liquids into the flask, but other than that, that's all we need to state. So there's a lot going on in this section. We've got our molarity calculations, how we use the molarity equation, and our dilution equation. You've also got how to prepare a solution from a solid and how to prepare a solution from an aqueous solution, a concentrated one. And we've got how to find molarity of different ions. So there's going to be practice with all of these pieces, even making solutions. So you'll have a little hands-on practice where you'll make a solution from a solid and from dilution. So you've got that to look forward to. Let me know what questions you have. Thanks.